All right, so differentiating more complicated functions. So this took place in class on Friday the 26th of May over 2 periods. So there's a fair bit going on here. So we're not going to be rushing through anything. All right, so introduction. There's a lot more to functions than the polynomials and related expressions. I'm calling that like x to the half is not a polynomial, but the fact that there's x to a power, so that's a related expression, right? There's a lot more to functions than that. For a start, there are trigonometric functions, and they're very different from those power functions. So question 1 takes a look at that. Then there are the ways that functions can be combined. So question 2 shows the 3 important ways in which functions can be combined, and the rest of the handout is about that. Okay, so let's start by writing the derivative, singular, of y equals sine x. So just a quick little investigation. Y equals sine x looks like that. It goes on forever and it's periodic. So the derivative has to be periodic as well, because the gradient there is the same as the gradient there, is the same as the gradient there, and so on. It has to be like a recurring gradient, right? What we have here is when you want to look at a graph and talk about its gradient function, have a look at where you can see horizontal gradients, because they mean that the derivative has to be 0 at these points. All right, now, and then have a look at the sign. So we've got positive gradient here, and then negative, positive, negative, positive. Okay, so when I'm going to use purple for the gradient function. So I need a positive value, let's say here, positive value, but it needs to go down to 0. And then I need negative values, but then it's got to go back to 0 here. And then it's going to be positive, but it's got to go back to 0. What you can see is that we end up with something like this. So it seems that if y equals sine x, then y dash is, let's just say, approximately equal to cos x, just based on the shape of what we've got here. It might be some multiple of cos x, or it might be something else funky, but it has to be periodic, and it has to go between positive and negative in the way that was shown before. Well, it just so happens that the gradient of sine x actually is cos x. There's no approximately equal to about it. Now, I haven't proved that, but I've demonstrated that that is a believable result. And for the rest of this sheet, we're going to use that, and on we go. All right, question 2. Find a naive and incorrect derivative for the following expressions. Describe the way in which each expression is complex. So a naive thing here, I've got y equals x cubed times sine x. A naive derivative would be 3x squared times cos x. So that's just taking the derivative of each and multiplying them together. Okay, that's wrong, right? So, but the whole point of this is to like recognize what's wrong. This one, y dash, so we've got x squared minus 4 over sine x. So let's just take 2x, the derivative of the top, over the derivative of the bottom, all right? So that's wrong. It's just being too simple. It's actually more complicated than that. And this one, y equals sine of x cubed plus 4x plus 1. So we could say the naive and incorrect thing, right? Derivative of sine is cos, and then the derivative of the inside is 3x squared plus 4. Okay, so right, that's wrong. All right, so we've studied what's wrong, and now we're going to learn what's right. But describe the way in which each one's complex. Well, the first one is a product. It's a product of 2 functions. Okay, the second one's a quotient of 2 functions. And the third one, well, this is a composition. All right, it's a function of a function. So basically, if you have an x value, first you have to evaluate this right? So that's a function. You have to evaluate that. Now you've got another value, and then you've got to shove that into the sine function. So it's one function wrapped around another. Another example of a function would be square root of 2x plus 1. So you've got 2x plus 1 as a function, and then taking the square root of something as a function, right? Or the log of sine x or something, right? We don't know much about logs at the moment, but in due course. Okay, so these are the three ways that functions can be combined to make new functions. You can have a product of them, you can have a quotient, and you can put one inside the other, right? Now, plus and minus, of course, you can add two functions to get a new one, but differentiating the sum of two functions, that's no problem, right? You just do it. Okay, question 3. Pay careful attention as I demonstrate how to find the correct derivative of these. So we've got A. So I've got y equals, I'm just going to write full working here, x cubed times sine x. So I'm going to write y equals u times v. So u and v are both functions of x. I'm going to lay this out here. So u equals x cubed, and v is sine x. Now, if I'm going to do some derivatives here, then I probably need the derivative of each of these. So this is u dash equals 3x squared, and v dash is cos x. All right. So now I'm going to switch to red pen. Here's the key. Y dash is vu dash plus uv dash. So every single one of these is used. They just have to be put together in the right way. Right, now I pronounce this vuv. So y dash equals vuv. You just need a plus in the middle. Right, vu dash plus uv dash. So I've got this is the v and the u dash, and this is the u and the v dash. Okay, so you kind of get used to writing this and then looking at them in that sort of order. So y dash equals, so vu dash, so that is sine x times 3x squared plus, and then uv dash is x cubed times cos x. All right. Do I have to write that any differently? No. I could factorise it if I want. So I could write y dash, I could take out an x squared, and then I've got 3 sine x plus x cos x. So when we use, this is called the product rule. When we use a product rule, we often end up with things that can be factorised. And it's often good to factorise them, but I'm not saying it's necessary. That's why I've put that in grey as like an option. Okay, so there we go. That's a correct way to get the derivative of a product. You write y equals u times v, you write out what all these are, and then you apply this, well, you write that and then apply that, okay? B, so I've got y equals x squared minus 4 over sine x. So that's y equals u over v, it's a quotient, right? U equals x squared minus 4, v equals sine x. U dash is 2x and v dash is cos x. Okay, now for what do we do with it? Well, y dash equals, well, this is vu dash minus uv dash. See how the opposite of a product is a quotient and the opposite of plus is minus. Now, if it ended there, that'd be awesome, but it actually has another detail. That's all over v squared. Right, so that's it, nothing more. So get y dash equals, right, so once again, got the v and the u dash, and then here I've got the uv dash, so the u and the v dash, right? So this is, so I know it's a fraction. I'm going to put the squared in, so sine x, so I've got sine squared x here. And now, right, v u dash, so that's sine x times 2x minus, and then x squared minus 4 times cos x. All right, there we go. there's nothing that can be factorised there or anything like that. So that's that. Okay, I'll just clear myself some room. And for question C, now this is quite different. So product and quotient are obviously related. You can actually get by without a quotient rule at all, and you can express everything as a product. So for here, you could have said y equals x squared minus 4 times, and then the times cosec x, right? So now it's a product, okay? I'm not saying that's a better way to do it, it's not, but I'm just saying that the quotient rule is really just a different expression of the product rule. But composition is completely different. If this is y equals sine x times that, then that's a product, but it's not. It's the sine of this. Very different indeed. All right. So y equals sine x cubed plus 4x plus 1. That's the all right. So that's the question. I'm going to simplify this by saying y equals sine u. Right, now there's no v here. That's y equals sine u. Now that is much simpler than that, all right? And I'm going to write down u equals x cubed plus 4x plus 1. And I probably need the derivative of that, but for reasons that will become clear, I'm not going to write u dash, I'm going to write du dx. So that's 3x squared plus 4. Okay, now I'm going to write the important thing in red. dy dx, so I'm not writing y dash. dy dx equals dy du times du dx. All right? Very different from the product and quotient rules. What looks like happened, this looks reasonable. It looks like the du gets cancelled out, right? And that's kind of true. These things are not actually fractions. They look like fractions. They behave like fractions in some ways, and this is one of them. The fact that you can take this and simplify it to just dy over dx, right? Now, it's more important at this point that you get used to like using this rather than thinking too much about the deep stuff going on. But here's how we use it, right? So dy du, right? Here's y equals sine u. So what's dy du? Well, it's cos u. dy du is cos u. And now du dx, I already wrote down, is 3x squared plus 4. That's got to go in brackets. Okay, so shall I use some colour here? I'm going to use some colour. Right, so that's that times that. Well, I've got that times that, right? Now, u is not going to stay like this. I'm going to replace it. So what I have is y dash equals cos of x cubed plus 4x plus 1 times, and then 3x squared plus 4. All right, so pretty complicated result, isn't it? Okay, but it's a complicated function, yeah? You could easily graph just this bit, and you can easily graph sine u, but there's no way that you can easily graph this whole thing. It's a complicated function, and so it's got a complicated derivative. All right, so that's example of product rule, quotient rule, and chain rule. And now the opportunity in question 4 is for you to try it yourself to follow the exact thing that we've just done. So you can pause for as long as you like and try it, and I'm moving on. So A. Right, I won't write the question, I'll just do it here. So y equals u times v, it's a product. So u equals 2x cubed plus 5, and v equals sine x. U dash is 6x squared, and v dash is cos x. The rule, y dash equals vu dash plus uv dash. All right, put it all together. So sine x times 6x squared plus, and then 2x cubed plus 5 times cos x. Okay, so that's fine. Nothing has to change there. I am going to tidy it up a little bit and just sort of write these in a consistent order. I'm going to put that before the trig thing, and I've got that before the trig thing already, right? So just 6x squared sine x plus 2x cubed plus 5 cos x. Okay, that's just a little bit tidier. So this one I was very directly doing the v u dash and then the u v dash. In reality, when you practiced at this, you'll kind of just look at them and go, right, I'll write them in whatever order I like. Okay. Right, so that's A. Right, B. So I've got y equals u over v, where u equals sine x and v equals x squared. U dash is cos x, v dash is 2x. The rule is VUV over v squared, right? Minus because it's a quotient rule. So plus goes with times and minus goes with divide. Right, so this equals, right, I know I've got a fraction, I've got v squared, I'm just going to set that up. So v is x squared, so v squared is x to the 4. Okay, vu dash is x squared cos x, then minus, and then I've got 2x sine x. Notice, like I put the v dash before I put the u. As long as I've got both of those things in any order, I've done that correct, and then that is tidy. Okay, nice and tidy. And now C. Right, so I've got y equals sine of 5x. So y equals sine u, and u is 5x, right? I'm just gonna write in like dy du is cos u, right? And du dx is 5. Like this could be a better way for me to set it out, right? So this gives us that, and that gives us that, right? So this is like the derivative of y with respect to u. The function is sine, so the derivative is just cos u. Never mind that u represents a function of x. When we get dy du, we're just treating u as a simple variable, not as a replacement function. Okay, so dy dx equals dy du times du dx. Right, so it's just cos u times 5. So that I'll bring the 5 out the front. That's 5 cos, and u is 5x. Okay, so there's the answer to that. But I want to look a little bit more. Y equals sine 5x, and y dash is 5 cos 5x. So I'd like to just do a little table. I did this in class. I'd like you to fit this somewhere, whether it's on separate paper or something. This is the function and this is the derivative. So like for instance, x cubed, the derivative is 3x squared, right? Okay, sine x is cos x. Sine of 5x is 5 cos 5x because we just did that one. So what do you think sine of 4x would be? Well, of course, it's going to be 4 cos 4x. What about sine of negative 3x? Well, that's going to be negative 3 cos negative 3x. Okay, so there's a pattern there that I want us to get comfortable with and not have to like do all this every time. All right. So just a remark about the chain rule. You'll use the chain rule less than the product and quotient rule as time goes on. What happens is you kind of notice that, when the function's like this, the chain rule says that the derivative, the derivative of that comes out the front, and then we get cos, and then, okay? You get the hang of it. I'm not saying that you should have the hang of it already, but you'll get the hang of it, and it's really important that a simple thing like this doesn't take us long to differentiate. All right, use the space to summarise the three rules. So we've written them already. So if y equals u times v, then y dash equals vu dash plus uv dash. And if y is u over v, then y dash is vu dash minus uv dash over v squared, right? And if y is some function of u, where u is a function of x, then dy dx is dy du times du dx. Okay, it's easier to like apply the chain rule than to like summarize it. I don't think anyone would look at that and go, oh yeah, I get it. Whereas these ones, yeah, you get it. Question 5. So try these. So it's just more practice. And note that we can get the derivative of sine 3x directly, right? So you should pause and try this before looking at my answers. I'm moving on. All right, so A, y equals u times v. So I've got u equals x to the 5 and v equals sine 3x. U dash is 5x to the 4. V dash is 3 cos 3x. So then y dash is vu dash plus uv dash. And so so I'm just going to put them in the order that makes sense. So 5x to the 4 sine 3x plus, and then uv dash. So 3x to the 5 cos 3x. Okay, so I looked at that, and I've put the 3x to the 5 cos 3x. Right, so notice from there to there, like, I just got that derivative nice and quickly. B. So y equals u over v, and I have u equals 2x plus 5 and v equals 3x minus 7. U dash is 2 and v dash is 3. So this one's a bit simpler. Right, y dash is vu dash minus uv dash over v squared. So that is, right, well, I know there's a fraction. So my v, that's 3x minus 7 squared. So I've got my denominator. Now, vu dash minus uv dash. So that gives me 2 lots of 3x minus 7, right? That's that and that. And now I've got this and this. So I'm going to put the 3 out the front. So minus 3 outside 2x plus 5. Right, now we're expected to simplify that. So 2 lots of 3x minus 3 lots of 2x is nothing. So I've got no term in x there. And then 2 lots of negative 7 minus 3 lots of 5 is negative 29. So that is negative 29 over 3x minus 7 all squared. All right. Okay, question 6. Oh no, I haven't done C. All right, so I'll... All right, question C. Right, chain rule, this one. Function of a function rule. I don't think did I mention it before? It's called the chain rule. Okay, so I have y equals u to the power of 4. Right, and u is 2x cubed minus x squared plus 4x plus 5. So let me write the little details. So dy du is 4u cubed, and du dx is 6x squared minus 2x plus 4. And to put it together, dy dx equals dy du times du dx. Just want to make a comment here. We're going to be using the chain rule quite a lot in an extension part of this topic, and the letters will typically not be y and x. Okay, so we've got to get comfortable with the structure of the rule and just using it carefully and correctly. Okay, so dy du, that's 4u cubed, and du dx is 6x squared minus 2x plus 4, right? And then just to expand out the u, so that is 4 lots of 2x cubed minus x squared plus 4x plus 5 to the power of 3 times 6x squared minus 2x plus 4. There we go. So pretty complicated. Want you to notice that there's a structure here that we're going to exploit here, right? So I had y equals something to the power of 4. And then the derivative, right, is 4 times the something cubed times the derivative of the something, right? So if you were taught that to differentiate this, you just do, bring the 4 out the front and change that to a 3 and keep that inside the same, you'd probably believe it, right? So that's what this is, okay? Seems reasonable. But to make it correct, you have to multiply by whatever the derivative of that is, okay? So we don't need to go through all this working. You do need to have gone through it so far so you understand what we're doing, but we can spot the pattern and exploit it. And that's what question 6 is about. So, just have a sip of tea. Yuck, overbrewed. All right, question C above exemplifies a common pattern. We've got some function raised to a power. So that is some function raised to a power. So the derivative of that is n times f of x to the n minus 1. So it's the same function raised to just a lower power and then multiplied by the derivative of what's inside, all right? So this looks complicated, but it actually means we can apply these things quickly. So I'm going to smash these in like half a minute. Let's see. So I get y dash equals 10 lots of x squared minus 5 to the power of 9 times 2x, right? The derivative of the inside. And then I get here y dash equals 7 lots of 9x cubed plus 4x to the power of 6 times the derivative of the inside, which is 27x squared plus 4. And then here I get y equals 3 times sine x all squared, then times the derivative of the inside. Okay, there, done. Right, now the only thing to do here is just to tidy up this one. So the 10 and the 2 combine to make 20, and I'll put the x in front. So that's x squared minus 5 to the power of 9. Right, and here I might put the smaller thing in front, like go from smallest to biggest, right? 27x squared plus 4 times 9x cubed plus 4x to the power of 6. Yeah, absolutely no big deal about making that change, all right? But that's one that you would tidy up. And here, there's nothing really to tidy up. That should say y dash, sorry. You could say y, instead of writing sine x all squared, you could write sine squared x cos x. Right, that would be more typical. Okay, so you can see that I was able to get the derivatives of these quickly without going through any explicit chain rule setting, because I'm recognizing that it's a function to a power. So the power, 1 minus the power, the original and the derivative, all right? You get the hang of it with practice. This counts as easy questions. Question 7. Here are 2 interesting results we can obtain. Now, I'm just going to do a third one, which I'm calling Z, because it comes before A, and so it like wraps around the alphabet and goes to the end. So I want us to find the derivative of cos x. And like I told you that the derivative of sine x is cos x, right? So what's the derivative of cos x? Well, I'm not telling you anything more, right? I'm not going to tell you what it is. We're going to work it out. The way we work it out is we'll express it as sine of, you know how it's 90 minus x or pi on 2 minus x, right? That's like the complementary angle relationships. And so now I can get that's y equals sine u, right, where u equals pi on 2 minus x. And if I put in my grey working, then dy du is cos u, and du dx, what's the derivative of that with respect to x? Well, it's -1. And so I get my dy dx equals dy du times du dx, which is cos u times -1, and then just tidy this up. So I'll put a negative cos, and then bracket, now the u is pi on 2 minus x. But what's cos pi on 2 minus x? Well, that's sine x. Okay, so basically, if y equals cos x, then y dash is negative sine x. All right, so we just learnt a new fact. I just want to point out, sine x differentiates to cos x. That differentiates to negative sine x. That differentiates to negative cos x. And then what's a derivative of negative cos x? Well, it's negative sine x, which is sine x. So it's actually, there's an infinite derivative loop there. You don't need to know that for this chapter, right? But that's just interesting. You won't see the derivative of sine x in this chapter. I'm just including it because it makes these questions more interesting, so it helps you to learn the material better. Okay, back to A. How do we find the derivative of tan x? So we'll write y equals sine x over cos x. And now that's a quotient, right? Y equals u over v. So u equals sine x, v equals cos x. U dash is now the derivative of sine x, cos x, and then v dash is negative sine x, right? Okay, now y dash is, right, so it's vuv over v squared. So y dash is, right, let me set up my fraction and my denominator. V is cos x, so v squared is cos squared x. Right, vu dash is cos x times cos x, so that's cos squared x, right? And then we've got minus, and now we've got sine x times negative sine x, so that's negative sine squared x. Now that numerator is actually cos squared x plus sine squared x, which is 1. Right, so that simplifies to 1 over cos squared x, and so we get y dash is sec squared x. Right, so y equals tan x has the derivative sec squared x. Pretty cool, isn't it? Look at the graph. Tan x looks like that. The gradient is always positive. Sec squared x is always positive because of the squared. Furthermore, the minimum value of sec squared x is 1. Right? Meaning the minimum gradient of tan x is 1. That occurs here, here, and here. Those are gradient of 1, and you can see that everywhere else it's steeper than that. Okay, that was fun. Last one here. I'll just do this. So y equals sine squared x. I'm just going to rewrite that as y equals sine x squared. That's a more convenient way to look at it for differentiation. So using the function to a power rule, the 2 comes down, keep the original to the power 1, and then multiply by the derivative of the inside. So that is just 2 sine x cos x, right? Now that, one of our extension identities, is that 2 sine x cos x is the same thing as sine 2x, all right? So the derivative of sine squared x is sine 2x, right? Now I'm just going to write this down, okay? The derivative of sine squared x is sine 2x. Now that looks like it could be a pattern, right? That maybe the derivative of sine cubed x is sine 3x, but that's not true, right? We found the derivative of sine cubed x here, and it wasn't sine 3x, okay? So this first one here is just an interesting coincidence. All right, so by this point, you might even have had a good break by now and decided you can't handle all this at once, but we've learnt, right, what have we learnt? We've learned about the derivative of sine x just so we can have more interesting questions. Where I demonstrated how to do, we looked at how not to differentiate these, and then we looked at how to actually differentiate them, right? Then there was a chance for you to practice on similar questions, summarise the rules, try some more, so more practice, and then to see how certain ones can be done more quickly, and then just some interesting results, okay? So now on to question 8. These questions all have a surd in them, right? And sometimes they're in a fraction. So we're going to put these into index form and then differentiate them. So for A, y equals x cubed minus 4 to the power of a half, and y dash equals half of x cubed minus 4 to the negative half. But we need to multiply by the derivative of the inside, so 3x squared. Now, there's, to tidy that up a bit, so that's 3 on 2 x squared and then x cubed minus 4 to the power of negative a half, right? Another way to write that, if you wanted to use a surd form, right, we need a fraction because we've got a negative power. So we've got the square root of x cubed minus 4 there. And then we've got a 3x squared on top, and we've got a 2 there. Okay, which do you like better, that or that? Okay, I prefer that one generally, but that's okay, right? But when we get to other things like turning it to that, just look a bit nasty. So just be aware that it can be both, and like you got to be capable of converting between them. Right, B. Y equals a cube root of that. So it's the same thing inside, but we're just doing the cube root. So we've got x cubed minus 4 to the power of a third. And now I've just made an interesting observation here. This is approximately equal to x, right? If you just take x cubed and take the cube root, you get x, right? This minus 4 is not going to have much effect when x is a larger number. So this function, whole function, is approximately equal to x. So we expect that the y dash is approximately equal to 1, right? Which is a derivative of x. Let's see if that happens. So y dash is 1/3 of x cubed minus 4. Now we need to drop that by 1. So that gives us negative 2/3, and then I need to multiply by the derivative of the inside, which is 3x squared. Okay, I did that here, I'll do that here. All right, and the 3 and the 1/3 cancel. I'm not going to literally cross them out because that's messy, but I'm just going to put x squared and then bracket x cubed minus 4 to the negative 2/3. And to make my point, I'm going to write that as x squared over x cubed minus 4 to the power of 2/3, right? Okay, I'll leave it like that. Now, x cubed to the power of 2/3 is x squared. And once again, the minus 4 will have an impact for small values, but it won't have much impact for large values. So this thing here, this is approximately equal to x squared over x squared, which equals 1. So yes, the y dash is approximately equal to 1, right? And so, anyway, I won't go, that's all the red stuff's an aside. The main thing is that we are capable of performing that differentiation. Okay, so let's clear that. Okay, C. So y equals sine 4x to the power of a half. And y dash is half sine 4x to the power of negative a half times whatever the derivative of sine 4x is, which is 4 cos 4x. Why 4 cos 4x? Remember way back here somewhere? There, right? There's a pattern there, okay? You need to get used to that. So we've got, the half comes down the front, we subtract 1, right? We keep that the same, but then we need the derivative of the inside. Right, the half times 4 is 2. I think I'll write this as 2 cos 4x over square root of sine x. That's the answer. Right, D. Take that question and rewrite it in index form. So that is x plus 2 to the power of 3/4. So y dash, we've got 3/4 x plus 2 to the power of negative 1/4, right? That's 3/4, take away 1. We need to multiply it by the derivative of the inside. The inside is x plus 2. The derivative of that is 1. Okay, so if we forgot to multiply by 1, it wouldn't have made any difference. But we need to remember that when we've got something to a power, we need to be multiplying by the derivative of the something. And so y dash is, well, there we go. That's a perfectly good way to write it. I'm not going to write it in insert form, but if I was required to, I could, right? So could you. Okay, E. Y equals 1 over square root of x minus 3. So I've got y equals x minus 3 to the power of negative a half. Right? And then y dash is negative a half x minus 3 to the negative 3 over 2. So subtracting 1 from the index, I need to multiply it by the derivative of the inside. And so that is this can just stay as it is. And F, right, this 5 here is like a coefficient that can come out the front. So y equals 5, and then I've got 2x plus 5 to the negative 3 over 2. All right, y dash is 5 times negative 3 over 2, outside 2x plus 5, take 1 from the index, that's negative 5 over 2, multiply by the inside, the derivative of the inside, and that's 2, right? That 2 cancels with that, and so we've got y dash equals negative 15 lots of 2x plus 5 to the negative 5 on 2. Okay, so I hope you did those yourself and got them all right. People in class handled them quite all right. Okay, question 9. The following questions combine 2 rules. So they're starting to look a bit more funky, aren't they? So this is a quotient rule, but the denominator to get the derivative is a chain rule, right? All right, we're going to need that. This is a quotient rule, a product rule overall, but we'll need a chain rule there. And this is a quotient rule, and we'll need a chain rule there. Okay, so these tend to get, questions that look like this tend to get reasonably messy answers, and that's okay. Right, so A. So y equals u over v. Right, we've got u equals 4x squared, v equals 2x plus 1 cubed. Right, u dash is 8x, v dash So careful here, we've got 3 lots of 2x plus 1 squared times the derivative of the inside. So we'll end up with 6 lots of 2x plus 1 squared. Our derivative, y dash, is VOOV over v squared. All right, so get my v squared right. So v is 2x plus 1 cubed. So v squared is 2x plus 1 to the power of 6. I think I'm being optimistic, only allowing myself that much space. I think it's going to take more. So v u dash. So that's that and that. So I'll write this as 8x outside 2x plus 1 cubed minus. Now, u v dash, oops, here's my v dash, but 6 4s are 24. So I've got 24 x squared and then 2x plus 1 squared. There we go. All right, no need to do anything to that. There's the answer. All right, b. So y equals u times v, and u is 2x plus 3, and v is 3x minus 5 to the power of half. U dash is 2, and v dash is half 3x minus 5 to the negative half times 3, which is just 3 halves, 3x minus 5 to the negative half. All right, so y dash is VOOV with a plus because it's a product rule. Okay, VU dash, so that one's easy. So 2 lots of 3x minus 5 to the power of half plus UV dash, so I've got 3 over 2, then I'm going to chuck in the u, so 2x plus 3, and then put in the 3x minus 5 to the negative half. All right, and that's the answer. So the UV dash, I had to take that and that, but I put it in the order of 3 over 2, then that, right? There's a lot of stuff here, so I just want to get a tidy answer up front. Okay, so I've done question B. Now I'll do question C. I think I'll just clear all this away. Okay, C. Right, so y equals u over v, where u is 2x plus 1 to the power of 1/3, and v is x plus 6. U dash is 1/3, 2x plus 1 to the negative 2/3 times 2. V dash is 1. Right, remarkable difference in the complexity of the two derivatives there. Y dash is VOOV over v squared. Right, let me get my denominator. Okay, VU dash, right. Oh, no, I didn't tidy this up. So that's 2/3, 2x plus 1 to the negative 2/3. That's a coincidence that these are like the same fraction. Okay, VU dash, I'm going to put 2/3, and then I'm going to put the x plus 6, and then I'm going to put the 2x plus 1 to the negative 2/3. Now I've got a minus. Now I've got UV dash, and v dash is 1, so this is simple. So 2x plus 1 to the power of 1/3. Right, and there we go. All done. Now, something I did in class was I gave the challenge of solve y dash equals 0. And I'm just going to do this for C, right? Not for all of them. So y dash equals 0 when... Now, have a look here and have a think. We have a fraction and then we want the fraction to equal 0. If you have a fraction equals 0, that means that the denominator equals 0. And also the numerator equals 0, the denominator doesn't equal 0. That's a subtlety. I'm just going to concentrate on if a fraction equals 0, then it can only happen if the numerator equals 0. So I'm just going to focus on this bit, all right? So y dash is 0 when 2/3 x plus 6 2x plus 1 to the power of negative 2/3 minus 2x plus 1 to the power of 1/3 equals 0. Right, now that looks awful. We're going to factorise it. What common factor is there? Well, not much really, but that and that have something in common that's not an obvious thing to factorise. So I'm actually going to pull this out, exactly that, as a common factor. So I'll get 2x plus 1 to the negative 2/3, and then I get 2/3 of x plus 6 minus, and then to get this part with that, what I need is to multiply by 2x plus 1 equals 0. Okay, so we continue. 2x plus 1 to the negative 2/3. Now I'm going to take out a factor of 1/3 here. And that gives me 2 lots of x plus 6 minus 3 lots of 2x plus 1 equals 0. By the way, if you think this is all ridiculously hard and don't care, that's fine. This is for a future topic, right? So we're doing heavy algebra here, not differentiation. The differentiation finished when we did that. I'm just giving a challenge question. So from here to here, right? I don't really like that fraction much, so I've pulled out the denominator. So I've got 1/3, and then to get that times that gives me that, right? And then to get this, we've got the 1/3 times 3. Okay, so now I've got 1/3, 2x plus 1 to the power of negative 2/3. Now this is 2x minus 6x, so that's negative 4x, and then I've got 12 minus 3, so negative 4x plus 9 equals 0. And so I'm going to multiply both sides by negative 1. I get 1/3 lots of 2x plus 1 to the minus 2/3, and then that's 4x minus 9 equals 0. So I've made this look as nice as I can. And now, what happens when we've got a factorised thing equals 0? Well, we can just go through and go, right, so either that equals 0 or that equals 0, right? So that would give me x equals negative 1/2 for the first bracket, or 9/4 for the second bracket, right? Wrong. So this one here is a no-no, right? And I'm doing this whole thing so that you can learn this subtlety. This thing here has a negative index, which means it's on the bottom of a fraction, right? So if we put negative 1/2 in here, then yeah, we can get this to be 0, but then we'll be putting that 0 on the bottom of a fraction. So this negative 1/2 is not a good solution. Okay, the 4x minus 9, yep, That's fine, that's good. So we've got x equals 9 over 4. Now, strictly speaking, let's just go back and look at our y dash, which is here, right? So if we put x equals 9 over 4, then somehow we manage to get 0 in the numerator. Luckily, we don't get 0 in the denominator, so we're all good. Now, what's the consequence of this? Y dash equals 0 means that you've got some horizontal tangent, which is going to presumably look like one of those, okay? There are other things that it could look like, but let's just assume it might look like one of those. So I have no idea what y equals the cube root of 2x plus 1 over x plus 6 looks like, but I'm going to tell you two things. Number one, the denominator grows a lot faster than the numerator. So it's going to approach the x-axis, right? It's going to approach 0. And secondly, it has a stationary point at 9 over 4. So it's probably going to look something like that. Now, what it does over here, I'm not really sure, right? So, okay, I'll just put a question mark. But I just raising this because, like, why are we learning about differentiation? Well, it helps us to find out things about the graph without having a graph, right? Or to find out, like, you know, what's the maximum possible value of this? What's the maximum possible y value here? Well, like, I'd need to do more analysis, but like, it's probably here at whatever that y value is, okay? 9 over 4 comma something, and that something's easy to find. So yeah, more analysis required, but this is just showing you, even though it was heavy algebra, the value of being able to solve y dash equals 0. All right, clear all this up. We didn't get any further than that in class, but I might as well just finish off because this is the last bit, right? And just point out too that you can work on very broad range of questions here. So don't focus on one exercise, do bits of each so that you're practicing a range of skills. You can always go back and do more of each one later. Okay, so question 10, the equation of the following tangents. So we've got y equals x plus 1 squared, x minus 1 to the 7, right? Now at the point 2 comma 9, I'll just differentiate first. Well, first of all, I'll write my y equals u times v. So I've got u equals x plus 1 squared, and v is x minus 1 to the 7. So u dash is 2 lots of x plus 1 to the 1 times 1, right? So the index is 1, and we multiply by the derivative of the inside. And v dash is 7 lots of x minus 1 to the 6 times 1, right? So y dash is vu dash plus uv dash, vuv. So that is x minus 1 to the 7 times 2 lots of x plus 1 plus x plus 1 squared times 7 lots of x minus 1 to the 6. Now I could maybe tidy that up a bit, but at 2 comma 9, y dash equals, so I need to just work out what the gradient is, right? So that is, so remember x equals 2. So I'm going to substitute into there and there and there and there, right? So follow along. So 2 minus 1, that's 1 to the 7 times 2 lots of, right? 2 plus 1 is 3. And then plus x plus 1 squared. So that is 3 squared times 7 times, and then x minus 1 is 1 to the power of 6. Okay, you could do all this in your calculator if you like, but that is 6 plus 63. 3 squared times 7 is 63, right? So 69, okay? So the gradient is 69. So we have now the gradient of the tangent. We have y minus y1 equals mx minus x1. We have a point of 2, 9. We have a gradient of 69, so we can just do the maths. So y minus 9 equals 69 lots of x minus 2. And y equals 69x minus 138 plus 9 minus 129, okay? So there's a gradient of the tangent, right? I think I'll leave that one to you. It's just a quotient rule and same sort of thing. And now last one, which has a slightly different focus. The curve y equals square root of x plus 3, which by the way looks like that, right? Has a tangent with gradient half. Now, gradient half means you go like across 2 and up 1. So that's a gradient of a half, right? So somewhere here it's got a gradient of a half. Okay, I'll try and, what I'm going to do, oops, is not that. What I'm going to do, I'm going to try to draw a perfect straight line that looks like about a gradient of a half. Now, if I can move that to be tangent to the graph, right? Now, the question is, oops, what point is that? And, okay, we're finding the point N. Okay, that's what the question is saying. And it's all without drawing a single diagram. So we have y equals square root of x plus 3 to the half, right? We'll take the derivative. Y dash is half of x plus 3 to the negative half times 1. Okay. So y dash is, right, half x plus 3 to the negative half, or 1 over 2 root x plus 3, whichever way we'd like it. Okay, now we're told, so given the gradient equals half, we will solve y dash equals a half for x. Okay, so y dash is in terms of x. So if we know that y dash is a half, the question is, what's x, which is there. So we'll get, all right, my only question is, do I want to choose that one or that one? Like, it doesn't matter. It's just what are you going to be more comfortable with? I think I'll choose the one on the right. Part of me wants to choose the one on the left, but okay. So solve y dash equals a half, right? Well, I can cancel out the 2's, like I can multiply both sides by 2. And then I can take reciprocals. Right, and I can square both sides. So x equals negative 2. And that looks, congruent with my diagram, doesn't it? And I've asked for the coordinates of point N. And so so y equals square root of x plus 3, which is the square root of negative 2 plus 3, which is the square root of 1, which is 1. Okay, so n is negative 2, 1. There's a complete answer to the question. All right, parts of it could be, set out a little bit better, but this is the end of a long video, so hope you'll forgive that. Okay, well done for making it to the end.